but I think they will appear.
It should be RU speed.
Okay.
Good,
okay.
good. Somebody's
Thanks
paying attention. Yeah. And there was also young meals, but since it's only half an hour, we'll see how much I go. So, thank you. So this is work done with my student, Nicolas Cresto, and there's a collections of paper about it. And in this talk, feel free, since it's one half hour, feel free to ask questions, and I can just adapt, to the, I don't exactly know what people know here and what's the kind of a level, and there might be a diversity of what people know. So it's okay to ask questions. I can go through the basics. So what I want to talk about is the fact that as we know that there has been, in the 60s, 70s, 80s, people studied this BMS symmetry. And we know that this BMS symmetry seems to control a lot about the property of the amplitudes. But recently, and even that is not yet completely understood, that is how much we can use BMS symmetry to kind of construct the proper asymptotic states. But since then, at the same time that people are working on trying to understand how to use BMS symmetry in properly defining the S matrix and the amplitude, we also realize that BMS symmetry is just the beginning of a long tower of asymptotic symmetries. Each one of these symmetries is related to subleading soft theorems. So this is where the story started with this work by Strominger and his team for the subleading symmetry, and then the sub-subleading symmetry. And I'm going to argue, in fact, in gravity, there's even a sub-cube leading symmetry, which is there, which is exact to a loop, or which is exact. I mean, which we have. And so. Now the question was, okay, what is the symmetry group then that extend this BMS symmetry group beyond just the leading one? The BMS group is really about the leading soft theorems. The subleading is about the conservation of angular momentum per point on the celestial sphere, and the subleading one is about a spin 2 charge. And then if we go beyond this object and we look at the charge algebra, we see that we have in the making a higher spin symmetry algebra, which people call LW infinity, which is kind of easy to see in the collinear limit of amplitude at the classical level. Okay, and so this LW infinity symmetry also has been seen, or was kind of discovered a long time ago by twistor people in the context of self-dual gravity, and in some sense understood to be responsible for the fact that self-dual gravity is an integrable system. So the integrability of self-dual gravity is due to the fact that there's this LW infinity symmetry in the background. And remember, every single integrable system that in nature is kind of an Hamiltonian reduction of self-dual gravity or self-dual Young-Mills. So in some sense, this is kind of the symmetry of all integrable systems. So it's kind of the biggest symmetry you can think of that organize these mathematical theories there. Now, where I came in is that I like to study. So these symmetries were first found in this amplitude business, looking at collinear limit, and but we can also do the usual analysis of asymptotic symmetry in terms of symplectic potential, Noether theorems, right? Looking at boundary condition at infinity and trying to see conservation of charges there. And so this is what we started to do with Daniele Pranzetti and Anna Maria Reclario, where we realized how to find this W symmetry algebra from the canonical perspective. And also recently, we kind of also studied the connection between this canonical perspective and the twistor perspective. So there's kind of a theme here. If you have questions about this general symmetry, so this is what I want to talk about. Going beyond BMS. Okay, and I hope I'll explain a bit more what this symmetry is about. So now there's a lot of this opens a lot of questions. Right? So first, and something which was the original motivation of work is that The connection, I mean, the establishment of this LW infinity symmetry in the amplitude sector is really at first order in G Newton, right? And you want to know whether it's possible to, I mean, having a symmetry in the free sector of the theory, okay, it's not such a big deal. You want to know whether there's something non-perturbative to that symmetry in the same way that BMS, has been established to be something which is a non-perturbative symmetry. And so, it was also not clear, in fact, what is this symmetry about? Like, what is it acting on in terms of the gravitational phase space? And what is its action? Okay, because as we're going to see, it's kind of a non-local symmetry in the gravitational phase space. So we're not kind of it's not a usual type of geometrical symmetry that preserve a locality. Okay, and then there's also, what I'm going to talk about connects a lot with this work by the group of Lionel and collaborators, where they also have understood how to construct these charges and the symmetry from a formulation of, from a non-perturbative twistor perspective. And a theme which is very important in the subject is a theme. So what I'm going to look at is these are kind of classical symmetry. And the question is, do they survive quantization? I mean, are these symmetries really, surviving the quantization? And then what we know is that the soft theorems are kind of getting deformed, right? When we quantize, they're kind of loop corrections to the soft theorems. And it's not yet completely clear whether these loop corrections destroys the symmetry or in fact should be kind of integrated into the symmetry. I mean, there is some work by essentially Laura and her team, and also Andrea and her team, which kind of suggests that, yeah, there should be kind of these loop corrections and these log terms that appears should preserve the symmetry. But I would say it's not yet completely under control. And there's the same questions of can we prove the conservation of this charge at I0, for instance, in asymptotic symmetry. So there's a lot of open question there. So but we first need to understand a bit more what this is about. So, okay, any questions? This was the very general introduction there.
Maybe also, Laurent, you could comment on the work of Beetleson and Costello about.
I'll comment later. Yeah. You mean, yeah. Yeah. No, I'll try to comment on that. Here I was commenting more on this work. That first started by Sao and Sen and his collaborator, where they found these log corrections to the soft theorems. These have been connected to by Laura and her team to somehow the usual kind of loop corrections which are there, and then Andrea is trying to understand what is the asymptotic symmetry perspective about them. So this is one thing about the loop corrections. Then later I talk about the question is, you have a classical symmetry, and we'll see. The question is whether this symmetry is anomalous or not at the quantum level. Okay, but let's, yeah. Okay. So I'll comment on the fact that yeah, the twistor people kind of if you take the twistor perspective. Anyway, it's more for later. So when you discuss symmetry, you need to understand what is the phase space of your theory, right? And the phase space of canonical gravity can be defined on any slice, but it can be, you can take your slice to be Scri plus, it's a very, or Scri minus. This is a well-defined Cauchy slice, and there you can understand what is the phase space about. And there's two types of data that appears in the phase space. So the first one is the radiative data, which is labeled in terms. Is there a pointer somewhere? All right. Okay. Yeah. So, which is a pair of, a complex shear. I mean, usually the shear is viewed as a tensor, right? But then you can view it, if you contract with CZZ and CZ bar Z bar, then it's a pair of complex scalars. So that's the language I'm going to use once you use the complex structure on the sphere here. And then the news, which is just the time derivative of the shear. Okay, so this is the radiative data, but that's not all the data you need at infinity. You also need the Coulombic data, and the Coulombic data is encoded into collections of charge aspects labeled by a spin S, right? So let's say S equals 0. A charge aspect is essentially an object that is defined at at any cut like that. It also depends on U. And let's say the spin 0 is the mass aspect. The spin 1 is the angular momentum aspect. The spin 2 is this new subleading charge, and etc. So there's this infinite tower of charge aspect that needs to be included in your phase space. And in order to understand what's going on, we know that at Scri we have a null geometrical surface, so we need to understand everything in terms of Carolean symmetry, right? And the nice, now we understand that the nice way to label Carolean field is essentially to label them by their conformal weight, delta, and spin S, right? And so what is this delta S? Essentially one way to define it, which is the simplest way, is just to look at, it was explained in the last week course by Tim, is just to view this Scri plus as some kind of projective space, and view the Carolean field as section around projective space with certain degrees of homogeneity. Okay, so lambda and lambda bar are the usual, spinor variable that, let's say, you could write as 1 over z. Okay, so this is the usual spinor variable, and U is a variable which is a weight 1, 1, homogeneity weight 1, 1. Okay, and so that's how you label the Carolean field, and then these weights here and spin, they control how these fields transform under supertranslation and superrotation. Okay, and it's very important. Yes. Well, I mean, we are going to see, so as we see, so let's look at the weight. So U, what is this operator du? Du is an operator that is going to take something of Carolean dat and map it into something of Carolean delta plus 1s, right? So the du operation, so a super translation will of course change the weight. Is that what you mean?
Right, but things also transform in a non-trivial way of the super translations, which is not able to just
yeah, so let's. No, but it doesn't matter. This contains both soft and hard. Yeah. Yeah. It contains here. I'm not yet splitting this into soft or hard. It's just Carolean fields, right? It's a very general notion. Yes. No, I'm not. Absolutely not. It's very important. I'll tell you when I am. No, I'm not. I'm talking about real gravity here. Well, we don't have symmetries yet. Okay, we just have asymptotic data. So I'll go there. Maybe keep your questions. Yeah, we're going to see what's true and what's not true and what's. Yeah, there's a lot of okay. we'll go there. I want to talk about the symmetry, but right now I'm just talking about like kinematical data, if you want, right? And so, okay, yeah. So, and this notion of Carolean weight is key. Once you understand, as in CFT, once you understand that weight, you can control the equations of motion. So for people who are not familiar with Carolean symmetry, and then, so it's good to know what is the Carolean weight of all the objects. So, I mean, C is an object of weight 1 and spin 2. It's a spin 2 object, and C bar will be 1 spin minus 2. The shear, of course, now becomes 2, 2. 2, 2 is the dimension of a stress tensor, so that's why the shear naturally plays the role of a CFT stress tensor, let's say. And then this object Q tilde, they're all of weight 3, okay, and spin S. So this is this kind of Coulombic data, okay. So if you're not used to, okay, so that's kind of the. That's kind of that. It's very important that to appreciate that really this is the full phase space. You need to include both. Okay. Okay. So what is the meaning of this Coulombic data? I mean, you're used to know what is the radiative data on the things, but what is the Coulombic data? So the Coulombic data is you can view them in some sense as the kind of sub-radiative data, the data that lies behind the radiation. This is the data that you will see at I0, but not necessarily this is the data you can peel off at I0 at space like infinity, right? Sky plus, I0, sky minus. So this is what I'm calling Coulombic. This is the data that kind of reveals itself there, And if you try to look at them on Sky Plus, you would find that they are kind of sub-additive. So let's say for people who are familiar with the Penrose-Newman notation, one of the things which is important in Newman-Penrose is just to look at the Weil tensor and then look at the component of the Weil tensor. The one which is psi2 is the one which really contains the Coulombic field. Okay, and the first term is Q0, will be Q0, will be the mass aspect. And then when you expand this, the next term will be d bar of Q1, and then d bar square of Q2, etc. And you will have this, if you assume peeling, which I'm going to do in that talk, this is how psi2 obtained, and then there's nonlinear corrections to that. Okay? Yes? So this is the thing which is under question or under review right now. How much of these survive in the absence of peelings, which is kind of if you include the logs. And so I think there's two types of logs. The log of R, I don't have much to say about the log of R, but there's the log of U. And I think the log of U, the evidence is, but that, the inclusion of the log of U can be done, but you need to add an edge mode structure to what I'm going to tell, okay? But that's kind of an open question. I think this is one of the big open questions in the field, which is related to whether the symmetry survive some form of quantization okay, so I would say this is a big open question mark. It's very interesting to look at. Okay, but there's two types of log, the log of R and the log of U, and there's some connection between the two. I'm not sure people agree on what's the connection yet, or and we can chat if the specialists there. The log of R are problematic for me, the log of U are not problematic as far as I can tell, but some people say that they're connected, so maybe, yeah. Okay. But that's what I'm looking. So if I look at peeling, I assume analyticity for the moment. This is what you would call, you could, yeah, okay? Yeah, if you call psi1, so then it would be the same thing. Psi1 will be the sum over S at infinity, and then it would be 4 plus S, and it would be minus 1 to the S of d bar. It would be exactly the same thing. D bar S, but then you will be a shift, QS plus 1. Psi 0 would be the same thing, but QS plus 2. Okay, so usually the dominant term of psi 0 is the mass, the dominant term of psi 1 is the angular momentum, the dominant term of psi 0 is the spin 2. And so if you just want to look at whatever the Penrose data pulled up on infinity, you already have 3 charges, like for free. Like there's no reason for you to stop at the mass aspect and angular momentum aspect. You need to include the spin 2. There's no, I mean, it's not optional. Okay, if you want to have the dominant structure in the psi's. Okay, so this is this Coulombic data, okay? And now this Coulombic data, of course, why don't we hear about it? Usually you hear that it's enough to give the radiative data. We don't hear about it because there's a constraints, right? The Coulombic data, as usual, that's the definition of Coulomb, is that they're kind of there's a constraint equation that relates the Coulombic data and the radiative data, okay? And this constraint equation takes this very simple and beautiful form here, okay? So let's say, can I erase that? You have the code. So this is this equation. It's kind of remarkable that for anyone that studied the complexity of Einstein equation, that you can, once you understand the Carolean symmetry and you work with really Carolean covariant fields, the things kind of simplify dramatically. Anyone that worked in Bondi coordinate and tried to solve an Einstein equation there can relate. It's interesting to see that this, you see, this term is kind of interesting here. The tilde means it's the aspect and then not the integrated charge. So, this object, remember, it adds Carolean weight plus 1, and this is a 3s. So this equation is, this object is a 4s object. D bar, it's, you know, it's 1, 1, 1 plus 3s minus 1, so it's also 4s. And C, we have seen it's 1, 2 plus, you know, 3s minus 2, so it's also 4s. So in the end, the Carolean symmetry says that up to the choice of coefficient, you have no choice on what the equations of motion should be. And if you demand invariance by supertranslation, boom, this is the only combination you can find, okay? At this order. So symmetry is kind of I mean, we are talking about gravity, and gravity, the equivalence principle tells us that the expressions of symmetry is dynamics, and we see that at asymptotic infinity. The expression of symmetry, Carolean symmetry, you need to add the supertranslation, boom, it gives you the dynamics. Okay, so these are the constraint equations. Yes? Yeah, you need to use you need to use a little bit some Carolean magic. Yeah. So what you're saying is that, I mean, for up to spin 2, no, there's just the Carolean component. So let's say at spin 3, you would have an object which is psi 0, 1, the first subleading coefficient, which is d bar of Q2, okay? And so you need to show, so, you know, this object is Carolean 3s, and this object is 3, 2, and this object is weight 2, 1. D bar, 2, 3, yeah, 2, 2, it should be. Spin 2, the D bar, I don't know, 2, 1, I think. Some Carolean, and then what you need to prove is this, whether this D bar operator on the, so there's the theory of when these D bar operator are invertible or not, and when there's a local part or a global part. So here on spin 2, it's invertible, in fact. If you were going to, sorry, no, this is D3. Okay, that's why. So okay, it's interesting. So this one, okay. We're going down to the nitty-gritty detail. So what you can show is that this object, yeah, which is an element D3, and this one is 2, right? So what you can show is that this psi 0, 1 can be decomposed into a psi 0, 1 global part, which is finite dimensional, plus a local part. which is in the image of this object, right? And the global part is conserved in time, and these are the Newman-Penrose charges. So I can always kind of play this game. In the component of the Weil tensor, there's some kind of global part, which and it's due to the fact that this representation of SL2C, they split, they are not reducible representation. Okay, is that clear? Okay. No. Oh, I mean, even for the sphere, yeah, for the sphere. Let's assume for the sphere. So even if it's not on the sphere, then let's say if it's on the sphere minus 2 points, I can even invert these operators. Yes. Yeah. So, okay, what Simone is saying is that this notion of invertibility of the operator depends on the topology of the sphere. So usually, if I'm a GR person, the sphere has no puncture, and then you have what you're looking at here is just the Gelfand decomposition of reducible representation. So when you have integer weight representation like that, the SL2C representations are reducible, and there's a canonical decomposition of them, and which is global and local. There's always a local part and a global part. Okay, now, of course, if you're in celestial holographer, or if you're a twister, you don't work on the sphere, you work on the cylinder, the sphere minus 2 points, and then all these operators are invertible. So this is, I don't want to dwell too much, but it's kind of well understood, okay? Any, good question. So sorry, but that's, so let's say if you're a celestial holographer, you don't care, you can invert 1 over Z minus omega is invertible. It's the inverse of D bar. Right? Yeah. Here, I gave you the definition in the expansion of the Weil tensor. Okay. Yeah, and they're defined such that this, and the way you can say it's a consequence of the Bianchi identity. This equation is, so let's say this equation is a consequence of the Bianchi identity. So let me say more. But up to now, I have the Weil tensor. You know, I assume peeling theorem. I just look at the component of the Weil tensor. Yeah. So up to spin 3, there's no dots. Okay. Up to spin 3. Okay. Let me say that a bit more. Okay. So this is what I say. So up to spin 3. Okay. So these are 1, 2, 3. The 5 first asymptotic Einstein's equation to all order ng Newton, completely non-perturbative. Okay? And so that's where I'm saying is that not only you have conservations of mass, of angular momentum. When I say mass, I mean mass aspect, mass per point on the sphere. I don't mean angular momentum, not just S2C. I mean angular momentum per point of the sphere. And then spin 2 and spin 3. This is a huge symmetry group, much bigger than anything you have studied in the context of BMS. Okay, so these are exactly the 5 asymptotic Einstein equations under the assumptions that I've taken care of the logs. Yes. No. Yeah. It's true at psi plus and at psi minus. They're both true on both. They're always, yeah.
Let's say you're applying the regulation just as per class, could there be initial data that describe the incoming radiation in these higher speeds?
Well, you can think, in fact, that this Q0, they are exactly the data that encodes the incoming radiation. I mean, so that the Cauchy problem is complete. Yeah. I mean, in some sense, yeah, once you go from Scri plus to Scri minus, there's going to be a nonlinear transformation. Perturbatively, it's easy to do. Like at perturbative, I can just, I can flip the radiative data as Scri minus. They're exactly the same thing as the moments of the charge at Scri plus. Okay, but non-perturbatively, it's more complicated. So Yeah, that's your question. Perturbatively, C plus, let's say, QS plus is the same thing as C minus, C bar minus, right? Morally. Okay. Okay. So, yeah, in the free theory. Yeah, that's what I mean. Yeah. Okay, so these are the first equations. The way you initialize them is that you say Q minus 2 is the time derivative of the shear, and Q minus 1 is the divergence of the shear. So these are the radiative data, and then below Q0, it's the non-radiative data. Okay, that's what I say. Mass aspect and moment aspect, spin theory. So what we're going to do pure gravity. It's still something to be done. I think there's no problem there. Is that we want to look at this, how these equations couple to mass. But right now, for the simplicity of this talk, I'm just assuming that it's pure gravity. So if it's pure gravity, QS of I plus is equal to 0. Right, and it means that I can these equations by integrating along chi. It tells me exactly what is the charge, and the symmetry charge is really the charge at I naught here. Okay. Otherwise, if there is a matter, then you just have the flux term here plus the art component of the charge at I plus. Okay. Right, in general, your charge QS. And think about if you're only comfortable with BMS, then it's going to be this integral of the flux, right, of some flux term, plus the charge at I plus, which is purely Coulombic, if you want. Okay, which is purely a matter-like. Okay. So if you want to go beyond, okay. I'll say more. So now if you go beyond spin 3, this is where you enter the realm of self-dual gravity, okay? So you could say gravity, these equations are exact up to spin 3. If I'm going to assume now, let's play the game that somehow they are valid for all S. I mean, the structure is so kind of natural. That's a very natural things to do. So now I'm extending my dynamical system to satisfy this condition. It's a much better approximation than the free one. The free one is when you drop the interaction term C. That would be the equations of motion for the free theory of gravity. Very trivial. To all order in S. So in perturbative gravity, these equations for all S are valid, okay? And then in self-dual gravity, it's kind of a better, think about self-dual gravity as a much better nonlinear approximation of GR, which is much closer to the truth than the free theory, okay? Okay. So I hope that answers the question earlier. Okay, so what's interesting to understand what I'm doing here and what kind of truncation I'm doing when I'm taking this equation, it's interesting to think of, you see these functional after I integrate them, they're going to be functional of the shear, C and C bar, okay? And in fact, you can show that they're going to be polynomial function of C and C bar. And so you can count the degree of this polynomial. And it's very interesting to introduce, to kind of split the Newton constant into an holomorphic component and an anti-holomorphic component. So if you think of G Newton to be the product of G times G bar, okay, then what you can do is you can use a holomorphic perturbative counting, right? And what you can show is that when you integrate these charges, you can show that these charge Q tilde, they are linear in G bar, okay? So they only depend on C bar linearly, but then they become to be polynomial in C, okay? So these charges are, I call them half perturbative. It's like they're perturbative in G bar, but they're non-perturbative in G, okay? And the degree here of the perturbation is 1 plus the integer part of S over 2. So let's say, so for spin 0 and 1, these are quadratic charge. And for spin 2 and 3, they're cubic, okay? So the quadratic component of the charge is called the odd charge, and the cubic one, we call it the super odd. And then if you go on, you will have more and more nonlinear corrections. And that explains why quantizing this theory might be tricky, okay? So the usual sector, that's why people focus on the usual sector, it's because the charges are purely quadratic and somehow it's simpler to deal with. Okay. That's what I was saying. You have this split into the soft part, which is linear, hard part, and the super hard part. And they represent the truncation. So the truncation is that you take, the truncation I'm doing is that imagine that you take Einstein's equation, okay? And instead of doing a perturbation in G Newton, I'm saying I'm staying non-perturbative in G, in the small g, but perturbative in G bar. Okay, and then that would be the equations to all order in G, but linear in G bar that you will find. Okay, and if you think about it, it's natural, it's connected to self-dual. So this is the connection between gravity and self-dual. You can view gravity, you make a semi-perturbative truncation, and it's self-dual because in some sense self-dual means that you are kind of non-linear in one type of the graviton, the plus helicity graviton, which is the G, but you're linear in the anti-self-dual graviton. Okay, so that gives you physical. It's usually not presented like that, but that's the way I think about self-dual gravity, not as a theory on its own, but a kind of a nice half-perturbative truncation. And then you can show that this equation in self-dual gravity, they represent Gauss conservation law. So in self-dual gravity, you have a formulation and you have a generalization of gauge symmetry, and therefore you have a generalization of Gauss law, and this is the Gauss law in self-dual gravity. Okay. I'm going very slow, but I think it's okay. So this is still the system of equations. So you know, essentially, what does it mean to have a symmetry? You have conservation law at Scri plus. You have you have conservation law, so you have a charge here that evolves. You have conservation law at I0, and then you have conservation law at Scri minus. So when I say conservation law at Scri plus, in fact, the charges they evolve there due to the radiation. Here, what you want to show to have conservation law is that to prove Noether's theorem, is that you want to have a notion of charge which is conserved when there's no radiation. If the charge is conserved when there's no radiation, you can look at what charge you get there. Then it will be considered at I0, because I0 by definition is defined as a place where you put a boundary condition where there's no radiation. Okay, so that explains the matching condition of Andy is simply charge conservation of Noether. Okay. Because I0 is by definition no radiation place. So, so we want to find out how to build from these objects charge which are conserved in the absence of radiation, and then the power of Noether theorem will go through full speed, and we are going to use that, and I can show you by full speed what it, how powerful Noether theorem is. Yes. Yeah. Yeah, that would be yeah. Well, then no, I think you need to think about interaction. I would say the way I think about it is that self-dual gravity or this nonlinear object, I think of it as a free particle, a representation of BMS or this bigger group, LW infinity. And then the S matrix is going to take care of that. Then there's going to be some nonlinear interaction, but it's starting at order what people would call G cube. I mean, you see, in that theory, the first order of interaction is very high, right? So the first interaction will be, the first four order in G Newton will be purely controlled by symmetry, and the rest is, so compared to what we saw, let's say the lecture we had last week about perturbation, I would guess that what they call PM3, right, which is 3 loop, okay, this would be the first order, because up to PM1, PM2, PM0, it should be all symmetry according to this counting. Of course, this has to be shown. Okay, but I'm not, so first we need to understand what first I haven't constructed the charge. I've just have this charge aspect, they satisfy this evolution equation. So the question is how do we identify the symmetry algebra and how do we understand its nonlinear interaction on the gravitational phase space? If I have that, I have Noether theorem, and then I can construct the corresponding Noether charge and prove the charge conservation. So these are the three things I want to do, okay? So I'm going to sketch. So the first thing is to kind of understand what we mean by boundary condition. So for people who are not specialists in the covariant phase space, they might think that, I don't know, covariant phase space, if you looked at papers, let's say 10 years ago, it looked like asymptotic symmetry was a very ambiguous construction. Today, and I think the course of Simone, the lecture of Simone explained that very well, it's completely non-ambiguous, okay? Once you tell me what you mean by radiation, there's a unique procedure to construct the charge and look at the conservation law. Okay, so the physical input is, of course, you need to know what you mean by radiation. What is radiation? Radiation, think about it as it's a boundary condition. So the condition of having no radiation is a boundary condition. And you want to be such that when you have no radiation, things are conserved. Okay, so, so technically, what does it mean? It means that the notion of having no radiation determines the form of the symplectic potential. And once I know the symplectic potential, Noether in 1915 told me, what is the procedure to do? It's completely linear. You know, people have almost forgotten that paper, how powerful that paper is. Okay, so what is an admissible boundary condition? Boundary conditions are not defined not at the fact that the symplectic form is zero, but the fact that the symplectic potential is zero. Right? The symplectic potential is PdQ, okay? And when you have a boundary condition, let's say, you know, if you have PdQ, if theta is PdQ, then, you know, like, your Neumann boundary condition will be P equals 0, for instance, you know. Okay, so theta is equal to 0. That's what it means. So what symplectic potential do we work with? So the one that usually people work with at infinity is the Ashtekar-Strobel symplectic potential, which is n bar delta C plus n delta C bar, integrated over Scri, right? And for this symplectic potential, the notion of boundary condition is that both n and n bar have to be 0. And this is too restrictive. Okay, so this is the usual notion of no radiation, but it's too strong. So what you can do is that you can play with, so what you can do is that the notion of symplectic potential is not unique, right? You can add a variation term that doesn't change the symplectic form, or you can add a corner term. Okay, and then so you're free to kind of shift this object in that way, pick your boundary condition. This freedom here is really the freedom in the choice of boundary condition. Okay, so defining the symplectic potential, defining the boundary condition is the same. And so the key idea here is to allow complex canonical transformation and write the symplectic potential. Remember here there was a 1/8 pi. It turns out that by adding a L and adding a corner term, I can change this symplectic potential to an holomorphic version, which is just 1/4 pi, n bar delta C. And this is the symplectic potential which maximizes the amount of symmetry. That's why I'm picking up. It's the one where the no radiation means that n bar is equal to 0, but n. So I free one helicity with respect to the other. N is arbitrary, okay? And so, okay, so this is, now we're looking for a symmetry charge. So this is the symplectic potential we work with. If you want, I can show you how you go from the first one to the other one by this corner term.
But are you now in complex GR?
I'm not in complex, I'm just making a, I mean, it's the same phase space.
Yeah, but I mean, is n bar the complex conjugate of n?
Yes, yes. So let me do it. I guess it's so, you know, you have 1/2. So you have this n bar delta C plus n delta C bar. You write it as n bar delta C plus delta of. I'm not going to do it properly, I guess. Let me. Sorry, there's minus 1/2. and then plus du of C delta C bar. And then you can work the right signs. Okay? So this is my delta L, and this is my du of theta. Okay? So of course, what I'm allowing here is complex canonical transformation, which is perfectly fine at the quantum level. It's like coherent states. At the classical level, well, okay, let's say that, you know, I'm doing these things for the quantum. So, okay, a complex canonical transformation is like going from a real polarization to a complex polarization. But it's the same phase space, okay? Except for this coordinate. Okay, so now what I get, you see what I get. I get a complete relaxation of what I mean by no radiation, okay? Of course, the challenge is to show, which nobody has shown, that this relaxation can happen at I0 too, okay? Which I'm not going to, which I don't know. Okay, so well, so you think that if you want to do gravity, then it's everything I say is up to spin 3, and then it's fully non-perturbative, okay? What you have to appreciate is the HTK-Strobel phase space is completely non-perturbative. There's no G-Newton expansion here, right? It's only a 1/r expansion. The radiative data of HTK-Strobel, when you express it in terms of the perturbative data, it's an infinite series in G-Newton, okay? So this is extremely powerful to work at I+. It's a non-perturbative formulation of GR, okay? What you're doing is truncating these things by the spin, okay? It's very important to appreciate. It's not a perturbative formulation. It's a non-perturbative formulation. The truncation I have now is this spin truncation. Yeah. Okay, so now I need to construct the charge. So this was the charge aspect, which are in 3S. I need to understand what is the symmetry transformations parameter, which I call, so it's going to be the same thing, tau, which is a series. Tau 0 is a super translation parameter. It's a Carolinum field of weight -1. You know, the super rotation is a vector, so it's a spin -1, and then you have a spin 2, and etc., spin 3, and an entire of charge. And you can, so what you can do is define this master charge, which is essentially the integral of QS times tau S. Okay, there's a correction term for Bondi. I'm not going to think about it as just this natural object. And what you can prove is that if you demand that these charges are kind of conserved when there's no holomorphic radiation, it gives you kind of a unique equations of motion for this symmetry parameter. So the new thing compared to the usual notion of symmetry is that you have to think in this in this asymptotic symmetry business, you have to think that the symmetry parameter is also kind of part of the phase space, in fact. That's why we're kind of struggling to understand it properly, because it's not just like, you know, well, because of that. Okay, so what's interesting is that, you know, they satisfy an equation which is kind of dual to the other equation, okay, which is this dual equations of motion here. So this is kind of a new notion, but it's extremely powerful to do that. I can tell you, for someone that has been doing this calculation of the spin 2 charge, you know, by hand and computing their bracket, it took me and Daniele and Anna a year and a half to compute the Poisson bracket. Now I can do it in a paragraph, like in less than a line. So this trick is extremely powerful. And I'm going to maybe explicitly write down what these charges are. Okay, so let's say. So, okay, so now we have to have this parameter that satisfies these dual equations of motion. Now, if you want to express the charges, you know, let's say you look at them at a given cut, the charge at a given cut. So if there's no radiation, these charges are conserved, so it doesn't matter where you evaluate them. And if you evaluate them at a given cut, you know, you're going to define this parameter. So the usual, the tau are U dependent, right? But let's say the value of tau at a given cut is just a function on the sphere. And then you can construct, if you want to get BMS, you just assume that the parameter tau2 and tau3 is 0, and you get BMS. If you want to go beyond BMS, so if you do that, you will find that Q tau 0 is just the usual expression, tau 0 of minus d bar square n, d square n bar. So is there bigger chokes? Where? Oh, here. Okay. Okay, there's slightly bigger ones, yes. Okay, thank you. Plus n bar, so this is the usual Bondi formula. Okay, so we have seen that. Let's look at the one for the angular momentum aspect. And as I said, you might go in the literature, people are confused about what is the angular momentum aspect. There is zero confusion. Like, you define for me the radiation, there's a unique notion of charge disappear. It's like all this literature where people are confused, they're confused, but there's no ambiguity at all. Okay, so I want to repeat that. For what is the angular momentum aspect? Noether theorem tells you, so this is the angular momentum aspect, T1. It's very important to do that because people who enter the field, they think that a lot of people are confused. Okay, plus 2n dc minus 3 plus u du d of n dc. Okay, and you might wonder why these two, why these three. It's literally the way the Carolean weight transformation under diffeomorphism. Okay, so I didn't write the transformation of how a Carolean field transform under superrotation, but the way it transforms under superrotation is that it transforms with a specific weight T1 times. Anyway, I'm not going to write it because I don't. But that's the fact that it's a conformal weight 3, okay, 3 plus u du. Something else than, there's only one flux that works, so whatever is the name of, is it the Stecker-Strobel? Yeah, maybe. Yes. It's the only one that works, there's only one. Okay. Yeah, but that's Walzupas. I mean, this is literally Walzupas. I said that once you have an n bar. Yeah, okay, so there's only, and then let's say if you write Q2, so you go there, Q2, let's say, let's do it because, and you see, okay, Q2, it's going to be a more D4 n bar. So you see there's a kind of a structure in the soft term. The soft terms of this. And then, okay, and then, okay. I mean, I'm just writing it to show you that whatever it is, n bar h. So I'm introducing, it's convenient to introduce h, which is du minus 1 of c, a non-local object. And then, okay. Just to show that it's completely explicit, d of n bar dh. And then there's plus 3 n bar. And then there's the nonlinear terms, which appears here, d bar square h minus c square duc. Okay? So, okay. So this is the full expression. There's the soft part, there's the hard part. I'm not claiming that you should make sense of it. It's just that to show you it's completely explicit. I can write down the Q3 and etc. discharge. Just to tell you that what we're going to do now is compute the algebra of discharge. Take the commutator of Q2 with Q2 and show that it's equal to Q3. If you do it by hand, which we first did it, it's a horrendous computation, which somehow works at the end by miraculous hypergeometric identities that you have no idea why it's true. So now that was the purpose of the goal, to show why these things, they close as an algebra. It's absolutely non-trivial, right, if you want to prove it. So, and it gives you the structure. This UDU is the natural Carolean weight structure. So this is natural from the Carolean perspective, but the nonlinear term are absolutely needed for the algebra to close. Okay, so this is where you see the discharge. They still start to contain nonlinear information. Yes?
So I think what is really answer know the algebra of the symmetry vector fields to be limited to like the tools.
Yeah, that's what we're going to show now.
Because then the fact that these clauses, that the verifiable clauses, it means that this unique construction is also implementing the effect of independence and covariance.
Yes, yes, yes. So this is what the purpose is. Okay, so just to show you, yeah. Questions? Yeah, you're non-local. You're non-local. It's true. It's full Einstein gravity. Up to here, this is full Einstein. Q3. If I go beyond, even Q3 is fully nonlinear. It's still true in nonlinear gravity that I have conservation law for Q3, and then behind I need this truncation. It's only at Q4 that I have to have. I'm starting to have n squared term. But I need, yeah, it's true that what is the symmetry? The symmetry, because the symmetry of a spin S symmetry as a vector field, it looks like something of the form, so it generates, so let's say T0 is du, right? T1 is dz, right? D. And T2 is d squared du minus 1. So you can continue. In some sense, Ts is going to be du minus, let's say if I go ts plus 1, something like that, right? No, it's self-dual. It's self-dual, yes. Yeah. Okay. But you see, it's much more powerful than just doing perturbative truncation. The perturbative truncation is that you drop all the quadratic term. That's the perturbative truncation. You only get the soft charge. Only the first terms. Yeah. Yeah, yeah, yeah. Yeah. But I'm happy to already understand up to spin 2 or 3. Even spin 1, there's still a lot of questions that people haven't answered. Because most of the study are in BMS. BMS is essentially spin 0 and the global part of spin 1. So, yeah. Yes? Well, it depends. So let's say if I'm in omega, if I'm in the Fourier transform, it would be 1 over omega plus I epsilon, right? Or if I'm in the real base, it would be integral from, let's say, you know, your cut, whether you want your cut to be to u. Okay, and there's very nice rules in integrable system. People have developed the pseudo differential calculus, so you can generalize Leibniz law and all these properties for. Exactly, it's a pseudo differential operator. So when you compute commutation relation, you just treat it as a pseudo differential operator, and that's, yeah. No, not for the algebra. What's going to depend on this prescription are the boundary terms, if they are, like the corner terms. But here, everything I say, I'm going to assume that my fields are Schwarzian. Okay? So then, of course, if they're not Schwarzian, and that's which I need to do if I want to include the logs, then I would need to go back to you know, pseudo differential calculus with boundary terms, which I think is interesting to develop. Hasn't been done, but. Yeah, but it doesn't matter. You just, if you treat du minus 1 as a well-defined object, it satisfies every identity. I can write down the you know. Yeah, I think I'm off my time. Well, okay, it's just, I mean, let me try to, I went slow, I think it's better to, so let me finish on the charge, let's say a little bit. So first, now I have this symmetry. How does this symmetry act? I mean, it has to be nutter, and it's not only have to have these things, I need to tell you how this symmetry act on the shear. And this is the formula. Okay, and these charges, you know, no matter how complicated they get, in the end, you can repackage the symmetric transformations on the shear in this simple manner. So the part which is red is the action of supertranslation, u du minus the d square of tau 0. The second one is the canonical way a diffeomorphism act on a field of weight 1, 2. Okay, so I cannot change that. The only part which is kind of surprising or new is how does the spin 2 object act on the shear. Okay, and the spin 2 generator acts non-linearly. And this, remember here I'm writing it very smart way because the tau 0 satisfies equations of motion. So strictly speaking, the tau 0 are kind of a they depend on u, and then they are functions of t0, t1, t2, t3, which are viewed as initial condition. But on the end, this is the action, and this is because you have this action, and you can check that it is really a full symmetry of your phase space here. So you need to check that. So it's absolutely not. So now let me just tell you just facts, right? Which are long calculations, but these facts are truth about this action. So this is your symmetry action. The first thing is that you want to show it's a symmetry. Okay, so if you take the commutator of two of these objects, you get a transformation of the same kind. Okay, so this you just have to do the calculation. There's no simple way. This is why it works, right? It works because this object closes under action. Okay, and then I'm going to read what is the symmetry algebra with this, double bracket here. Okay, that's the first fact. The second part is that the symmetry preserves the equations of motion, so it's a symmetry. You look at the equations of motion and you act on it and you get a transformations of the equations of motion. This is absolutely non-trivial here, okay, where these coefficients appear, but so it's a symmetry of the equations of motion. Remember, I didn't derive it by saying this is my Lagrangian and here is, if I add that, all of this property will be true, right? But I'm revealing this non-local symmetry from the canonical analysis. So this is a symmetry, preserves the equations of motion. And the last thing, which in fact is, if you know Noether, is simply a consequence of that, from what we have said, is that this symmetry, there's a charge. This symmetry is canonical, and the charge we have constructed, remember this Q tau, which is this sum over S of integral, of Q tilde S tau S at the sphere I0, okay, is the canonical generator of symmetry. Okay. Okay, it's a summary of a long calculation, but if you think for a minute, this is kind of quite remarkable. That you have this. Why is it not remarkable? Because you have a symmetry action which is nonlinear on the phase space, but still kind of closes, and non-local if you want in terms of this du minus one, but it still closes. So no, there's no, because the factor of 2 is simply because I'm holomorphic. So it's, yeah, the factor of 2 is simply that the holomorphic supertranslation and the anti-holomorphic are kind of independent. Yeah, we understand that. It's a second class constraint. When you put the real, anyway, no, there's no ambiguity there. So we have a compact expression for the charge as which means that if I assume that there's no matter at I plus, then I can get them as integral of n bar delta tau c along scry. Okay, so that's how which is the only expression that is covariant. If you think for a minute, okay. Okay, which is the usual expression for an auto-charged PDQ. Okay, and then so if you explicitly write it, this is the type of expression, and then when you solve the dual equations of motion, you get the entire of charge expression. Okay, so here is the algebra. So, and I'm going to try to conclude on LW infinity, and that's it. So this is the algebra. So the algebra of tau and tau prime of S, there's a part in blue here, which is the the flat space contribution. Think of it as these are higher spin field. Higher spin, higher spin vector field have a natural canonical symmetry, which is the Frolicker-Arrhenius in mathematics, where you can take commutator of two higher spin derivative, you get a higher spin derivative. So this is like this is a generalization of vector field. For people who know, the only thing is that the Frolicker-Arrhenius will not have this +1. So the gravitational makes it more complicated. And because you have this +1, you need to correct this term by this nonlinear term here. Okay, so if you assume for a moment that C is just a background parameter, you can check that this object satisfies Jacobi identity. Okay, so this is a proper well-defined Lie algebra if you treat C as a background. And then, so this is the other property. Well, the other thing is that you want to show that if you take two objects that satisfies the dual equation, remember this tau, this satisfies dual equations of motion, so you want to make sure that your bracket preserves the equations of motion, and it does. Okay. And it satisfies the Jacobi identity, and it provides a canonical representation of the algebra. Okay, so this kind of follows from, so that's your symmetry algebra. So a lot of information to take, but it's for anybody that works, like it's very, very condensed information there. Now, okay, I say if C now is not a parameter, you see, I'm now C is is not fixed. Then you have this variation there, and what you have is not an algebra; it's an algebroid. And I don't really like algebroid because I want to use algebra to quantize. Algebroid are not good for quantization. So let's look at but there is a natural sub-algebra inside here, and this is where we get W infinity, and this is where I'm going to conclude on it. So just a bit of philosophy, why do we have algebroid and not algebra? Is that we're talking about radiative phase space, right? So when you have no radiation, you naturally have a symmetry algebra. When radiation comes, your symmetry algebra transits from one state to another, right? It changes the parameter, like the structure constants of your symmetry algebra. That's the way you should think. And then you end up into another symmetry algebra. So this is a symmetry algebra labeled by the shear C0. And then here you have a symmetry algebra labeled by the shear C1. And then, and of course, because of the memory effect, and let's say at I+, you have the symmetry algebra labeled by the shear C equals 0, which is really the symmetry algebra that people like Andy or in perturbative you look at, right? You look at the symmetry algebra in the background of no shear. But of course, the memory effect tells you that different non-radiative cuts have different value of the shear. And so what is the symmetry algebra at a non-radiative cut? It's what we call the wedge algebra. Okay, so that goes back to your original question. What is the wedge algebra? Is the part of the symmetry algebra that preserves your shear. That's the wedge algebra. If the algebra preserves the shear is an extra parameter, and your algebroid becomes a symmetry algebra, and your theory at non-radiative cut has to be at the quantum level a representation of that symmetry algebra. So okay, so it means that C, you can treat it as some external parameter, okay? Yeah, you're killing a lot. Yeah, that's the symmetry algebra. This is the LW infinity. So let's go. What are you getting? So suppose that you're at I+, okay? If you're at I+, your symmetry algebra is W0S, and it's the space of T, which are in, weight -1 minus S, which are such that ds plus 2 of Ts is equal to 0. That's the wedge algebra. So what is this algebra? This algebra, it depends on the topology of the sphere, okay? So if the sphere, let's say, which is Sn, if the sphere has no puncture, this symmetry algebra is simply Poincaré, okay? If the sphere, let's go, has two puncture, then this symmetry algebra is LW infinity algebra. Okay, which is an infinite dimensional algebra. And it's not surprising, it's exactly what happened with the conformal symmetry. If the conformal symmetry is on S0, then it's SL2C. The conformal symmetry on S2 is Vira-0. Okay, so what is this LW infinity algebra? It is a localization of Poincaré in the same way that Vira-0 is a localization of Lorentz. And it tells you that if you want to localize Poincaré, you need that. This is kind of a universal symmetry algebra. And then, of course, it makes sense at the quantum level, because at the quantum level, you get scattering amplitudes where you place points on the celestial sphere. So the objects you have is S minus the location of these points. So that's why this is the symmetry algebra that's activated. And it's exactly like in CFT, a global symmetry of the vacua becomes, when you look at insertions of operator, a local symmetry. SL2C to Virasoro, except that here it's Poincaré to LW infinity. Okay, so that's, for people who like this axis, this is the new kind of axis for gravity. And then if you go for Sn, well, like here, you have it's not Virasoro. If you have 3 points, you no longer have Virasoro. You have a generalization of Virasoro, which is called Khrushchev-Novikov algebra, which people have studied. This is the algebra of symmetry of strings. And here you have the same thing. So it's not like there's one symmetry algebra. You see, W infinity algebra depends on the structure. So you can view W infinity algebra as the algebra around a local algebra around a puncture. You know, you insert your particle here, and then this is the algebra that this guy is. And so that's all I had to say. Yeah. Okay. And then, okay, maybe what we have to finish is that now what we have is a deformation of this algebra in terms of the shear parameter, and which is really what these things is about, is that the notion of vacua at zero shear, like the vacua at I plus, is not the same as the vacua at I0, because they're labeled by different shear. And so the algebra at I plus, which is LW infinity, is not exactly the same as the algebra at I0. It's another W infinity algebra, but rotated or translated by this shear. Thanks. Sorry I went overboard.
Okay, thank you very much. So maybe we should have had 1 + 1 slots, not 30 + 30. But still, if there are, let's say, a couple of additional questions, they're welcome. Please. Okay, I think we can thank Laurent again.